Okay, I'm going to talk to you about the binomial theorem now. Last night we talked about summations and proof by induction, a little bit of review of that. And then we talked about combinations the week before. So that's all going to kind of come into play for the binomial theorem. What's the purpose of the binomial theorem? First, let's just start off with an expression here. X plus y to the n power. When I expand something like this, for example, if n is equal to 2 and we have x plus y squared, that's fairly simple because in that case I can just go x plus y times x plus y. I do my distribution properties and I get x squared plus 2xy plus y squared. So in that case, it's really not too bad. But what if n is equal to 5 or n is equal to 10? It gets a lot more complex at that point. If we have x plus y to the 5th, suddenly we have 2 to the 5th combinations. Notice I said combinations of multiplications to do, and that takes a lot of time. Then it's going to be even more if I'm doing it to the 10, if I'm doing it to the 100, whatever the case may be. You can see it adds up very quickly. So the binomial theorem just gives us a much simpler way to expand something like this, and just a much easier form, and something that can be used for a lot of other things as well. So what the binomial theorem tells us is that x plus y to the n, which is written right here, is equal to the summation of k equals 0 to n, there's our n, of n choose k, there's a combination, remember we talked about combinations last week, times x to the n minus k times y to the k. So we're just taking our sum from k equals 0 to n, we're doing a combination, we're multiplying a few things, and that's going to expand the whole thing for us in a much cleaner fashion than what I was doing before. So you can kind of think about the concept of this without even proving it. You think about it because you're multiplying a bunch of x's and y's together, and so here you're going to do every combination, starting like if n were 5, you would have 5 minus 0, so you'd have x to the 5th, you'd have x to the 4th, x to the 3rd, x squared. You're also going to have all the y's because k goes from 0 up to 5, and you're going to have all the combinations of those multiplications, which is what a combination is. So it makes sense that you would use combinations in something like this. But what I'm going to do is I'm going to use a proof by induction to show you that this is true. And there's a few ways you can go about proving this, but I think that the proof by induction is a really nice way to do it. So let's leave that there. And if you remember, with proof by induction, we start with our first step, which is proving it for one case. And then we're going to prove a statement after that. And we're going to say if it's true for n minus 1, then it has to be true for n. We're going to make sure that that statement's true. In this case, we want to start with n equals 1. Let's just start with n equals 1. So basically we're going to prove this for all integers where n is greater than or equal to 1. So let's just start with that. N equals 1. Let's plug it in and see if it's true. X plus y to the n is just equal to x plus y to the 1, which is x plus y. Okay, so we've shown what that's equal to. Now let's show what this statement's equal to. We're saying n equals 1, so we're going to do the summation from k equals 0 up to 1. N is 1, so 1 choose k of x to the 1 minus k, y to the k. Now we can just plug in our k's and solve for that. So I'm going to bring the sum down here, and we have first starting at 0, so we have 1 choose 0 of x to the 1 minus 0, which is 1, so x to the 1, which is x, y to the k, which is y to the 0, plus, what's our next k? We increment up to 1. Sorry, I don't want a summation there. We want 1, choose 1 this time, of x to the 1 minus 1, which is x to the 0, y to the 1. 1 choose 0 is just 1. That can be shown by, remember we talked about a combination before, so we knew, let me just write it up here, we knew that n choose k was equal to n factorial over k factorial times n minus k factorial. So if you were to plug those in, you would do 1 factorial, 0 factorial is defined to be 1, 1 minus 0 factorial is 1, you're going to end up getting 1. So you'll find the same case for 1 choose 1 is also 1. So we're left with x to the 1, which is x, times y to the 0, anything to the 0 power is 1, plus 1 times y. So we're left with x plus y. What did we get here? We got x plus y. What do we get here? We got x plus y. So we have proven that these two sides are equal for n equals 1. We've proven it for one integer. Now, let's consider the next case. Oh, it looks like my power's low. Let me close this thing. Okay, there we go. So now what we want to do is we want to say, we want to assume that the statement is true for n minus 1. And then we're going to see what happens with n. So we're going to say assume the binomial theorem is true for n minus 1. We don't know that it's true for n minus 1, but let's just assume it is. And then what could we imply from that? If it were true, if we knew it were true for n minus 1, what could we say? We could say that x plus y to the n minus 1, we could say that's equal to the summation of k equals 0 to n minus 1, because now we're using n minus 1 instead of n, of n minus 1 choose k times x to the n minus 1 minus k y to the k. Right? Because I just took the binomial theorem and replaced any n with n minus 1. So we're assuming that this statement's true. Now, our goal is to prove that if we knew this was true, then we would know it's true for n. And if we did that, we would prove the whole thing by induction, because then we'd have the domino effect of 1 being true, 2, 3, 4, 5, all the way to infinity. So we started with that. Now, we know that's true. Consider for a moment x plus y to the n. Oh, there's like a bright light right there. That's unfortunate. Hopefully you can kind of see it. I'll try to avoid that light if I can. Consider x plus y to the n, just that expression. How can we write that? We could factor out an x plus y if we wanted to. We know that that's equal to x plus y times x plus y to the n minus 1. Right? Because x plus y to the 1 times x plus y to the n minus 1, you add exponents when you're multiplying, and we'll get x plus y to the n. Well, we've assumed something about this right here. We've assumed that's equal to this summation, which is the binomial theorem piece. So we're gonna go ahead and plug that in. So that is equal to x plus y times this piece. And actually what we're going to do is we're going to plug it in and we're going to multiply out, because we're going to multiply x times that and we're going to multiply y times that. So this is equal to x times this whole summation. And actually, even instead of writing all that, let's even just sum this in real quick. So if we multiply x by this, we're multiplying x by a summation, right? So x gets multiplied by every term in here. So we can just bring the x to the inside. And if you multiply the x times this whole thing, you would have x to the 1, and you have x to the n minus 1 minus k. So we could add the exponents, we'd be left with x to the n minus k on the inside there. So let's just go ahead and write that. The summation from k equals 0 up to n minus 1 of n minus 1, choose k, x to the n minus k, y to the k. Similarly, I'm going to go ahead and multiply my y in. So we are adding these two, so we're going to add it. So plus the summation. This is getting low here. I'm going to have to erase pretty soon. Summation of k equals 0 up to n minus 1. And this time we're multiplying the y together, the y's, so we're going to have y to the k plus 1. So I'm going to have n minus 1, choose k, x to the n minus 1 minus k, y to the k plus 1. So that's a plus statement right there. Now I'm going to have to erase the board to create some space. Okay, so now I'm going to go ahead and write this. Let's just think about this second expression right here. And let's write that a little bit differently. So remember, I still have this first part. I'm just thinking about this second expression. If I wanted to, I could write this as the summation, and instead of using k, I'm going to use j. I can use whatever variable I want. I'm going to switch back to k later, but you'll see why. So I'm going to go j equals 0 to n minus 1. And then I have n minus 1, choose k, which would be choose j here. Another way we can write that, if we wanted to, would be j plus 1 minus 1. Right? Because that's the exact same thing. That's just saying 1 minus 1, which is 0. So really that's just j. And then here we have x to the n minus 1 minus k. We can write that a little bit differently. We can do x to the n minus j plus 1. Right? Because that would be n minus j minus 1, which is n minus 1 minus k, which is now j. And then finally we're left with y to the k plus 1. Sorry, not k, j. J plus 1. Okay, so now that we've got that, we're going to rewrite that in one other way. Yeah, so now that we've got this, we're just going to rewrite this a little bit. The reason I used the j was, think about it, if you put a 0 in, you're essentially starting that parenthesis with a 1. If you put a 0 in there, you're starting with a 1. 0 in there, you're starting with a 1. So we could rewrite this so that our incrementer starts with a 1. When you plug in n minus 1, you're left with n minus 1 plus 1, which is n. Same here, you'll be left with n and n. So we could start it at 1 and end at n instead of start at 0 and end at n minus 1 and rewrite it a little bit. That's why I switched to a j, and now I'll switch back to a k. So this is just equal to the summation of k equals 1 up to n of n minus 1 choose. There, right there is our, that's our k basically. So we're saying k minus 1, because when you plug in j is 0, you're left with 1, and we're starting at k equals 1. So we're left with n minus 1, choose k minus 1, x to the n minus k, because we're choosing that to be k, we're starting with 1, and then y to the k. So we replaced all our j plus 1s with k's, and we're incrementing just slightly differently to account for that plus 1. Okay, so I've rewritten this into a new form. Now this is starting to look strangely familiar to our first term over here, which is exactly what I wanted. So if you think about this, I'm now, remember, I just rewrote that circle to look like that. I'm now going to kind of combine these two. And this is going to squish into the middle here, and then I'm going to erase it all, and then we'll get a clean board. But think about this for a second. The incrementers are slightly different. We start at k equals 0, we end at n minus 1. Here we start at 1, end at n. But we have an x to the n minus k and an x to the n minus k. We have a y to the k and we have a y to the k. So I can actually go ahead and combine most of the terms. If you think about it, we're actually overlapping on these sums from k equals 1 to n minus 1. We're only different on the 0 and the n. So let's not think about the 0 and the n for a second. Let's just think about what we can combine. We can combine k equals 1 to n minus 1. Those are the pieces that overlap in the sums of n minus 1, choose k minus 1, plus n minus 1, choose k. That was a bad parenthesis, there's my square. Times, there's our common factor. And let's just erase this here. Times x to the n minus k. Y to the k, right? Because if you multiply this out, the n minus 1 choose k minus 1 times that, you're left with, that times that, you're left with that piece. Plus, if you multiply out the n minus 1 choose k times that, you're left with that piece. So we've combined the two sums completely except for the 0 and the n. So let's think about those two cases. So when k is 0 down here, we're left with n minus 1 choose 0 times x to the n, because n minus 0 is n, times y to the 0, which is 1. N minus 1 choose 0 is just 1, so we're actually left with, so I'm going to add the addition, we're actually left with x to the n. We can think about the case of n now. What happens when k is n? That's our other extreme case. When k is n, we're left with n minus 1 choose n minus 1, which is 1, times x to the n minus n, which is 0. X to the 0 is 1 times y to the n. So plus y to the n. Now we've combined everything into this expression right here. So let's go ahead and make some room. Okay, so we're getting closer. Now what I want to do is I want to take this inside expression right here and I want to kind of simplify that. So let's go ahead and write that down. N minus 1, choose k minus 1 plus n minus 1, choose k. Let's think about another way to write that. We can actually use the definition of a combination to start off. So let's just write that out. N minus 1 factorial divided by k minus 1 factorial times that minus that factorial. So n minus 1 minus k minus 1 factorial. That's just using the definition of a combination. So we're going to do the exact same thing here. We're going to be left with n minus 1 factorial over k factorial times n minus 1 minus k factorial. Let's just go ahead and clean it up a little bit. So we're left with n minus 1 factorial over k minus 1 factorial. Here we have a minus minus 1, so we have a plus 1, which cancels with our minus 1. So we're just left with n minus k factorial. Okay, so here, there's not a lot we can do with that. So, okay, so now we're going to try to find a common denominator. What if I were to multiply this by k over k? I'm allowed to do that because k over k is 1. So in that case, I'm just going to put times k. And then here, what if we multiplied that by n minus k over n minus k? So we'd be left with n minus 1 factorial times n minus k over k factorial times n minus 1 minus k factorial times n minus k. Okay. Now, the cool thing about this is we can combine k minus 1 factorial times k is the same as k factorial. So we can rewrite this as k, sorry I'm coming down here, k times n minus 1 factorial over k factorial times n minus k factorial. And you'll notice over here, n minus k times n minus 1 minus k factorial is the same as n minus k factorial, because we're just doing the next integer up. So here we're left with n minus 1 factorial times n minus k over k factorial times n minus k factorial. Now we have a common denominator, so we can add the fractions together. If we add these two pieces together, if you look at the top, we're going to be left with n minus 1 factorial times k plus n minus k. Well, the k's are going to cancel, so we're going to be left with n times n minus 1 factorial, which is the same as n factorial. So that's fantastic. That means we're left with n factorial over k factorial times n minus k factorial, which is equal to, what is that equal to? N choose k. So this mess right here, which is right here, is just equal to n choose k, which is pretty amazing. So we've simplified that, and now we're going to rewrite this. So let's leave this here and just remember that this inside expression is equal to n choose k. Okay, so we can now rewrite this as the summation of k equals 1. That was not a very good summation symbol. Up to n minus 1 of, we said that's n choose k, times x to the n minus k, y to the k, plus x to the n plus y to the n. Okay, well, let's combine these two into the summation. If you think about if k were 0, if we added another term in there, what happens when k is 0? N choose 0 is 1. X to the n minus 0 is x to the n. Y to the 0 is 1. We'd be left with x to the n. So boom, we can add that in by just putting a 0 here. What happens when we increment this all the way up to n instead of n minus 1? We'd be left with n choose n, which is 1, x to the n minus n, which is x to the 0, which is 1, times y to the n. So we're left with y to the n, which is that piece. So this is just equal to k equals 0 up to n of n choose k, x to the n minus k, y to the k. And what is that? That is what we were trying to prove. That's the binomial theorem. So we were saying, we started with, let's assume it's true for n minus 1. If we knew that, if it is true for n minus 1, we've just proven that it is actually in fact true for n. So we've proven the entire thing because we proved it's true for 1, and we proved the statement that if it's true for n minus 1, then we know it's true for n. So we start with 1, then it works for 2, then 3, then 4, then 5, then 6, then 7, and it goes all the way to infinity. So we have just proven the binomial theorem. And next time, we are going to dive into some calculus, and we'll end up using the binomial theorem later. So this is a fantastic thing to use, very much simpler for expanding these things and a much simpler way to write things. And thanks for joining me with the proof of the binomial theorem.